This is your introduction to regression. Consider a bivariate dataset comprising of the variables x and y and the corresponding values associated with them. This being a bivariate dataset, we can of course plot it on two axes. One axis being the corresponding to the input variable x and the other one corresponding to the target or the output variable y. And when we plot the data, we can see that the data lies approximately on a linear trend. And so we can potentially fit this data set with a straight line. And what we're doing with a straight line is that we are saying that the target variable is the slope times the input plus some intercept. And that's parametric regression, where we're assuming that the data follows a parametric form. In this case, the parametric form is a linear fit to the data. Uh, so we make a choice of one specific straight line, as you see in the picture. And in this case, visualizing the data set, we can see that perhaps this is not the best fit to the data. Well, how do we quantify fit to the data? That's by evaluating the residuals or evaluating the errors. In other words, the errors are nothing but the difference between the model predictions and what the data is telling us. For example, we may want to consider the point corresponding to x equal to 1. And for x equal to 1, the model prediction y hat is negative 1.5 and the data is 2.74. So the difference between the model prediction and the data, whole thing square, is going to be 2.74 minus negative 1.5 whole thing square, which gives us an error of 17.99, a squared error of 17.99. We can continue to compute this for another point for x equal to 3.5. In this case, the model prediction for x equal to 3.5 is y hat equal to 2.25 and the data is 5.88. And the difference squared between the model prediction and the data is 13.19. We can continue to compute these differences for other data points as well. And for x equal to 6, the difference is 0.8. Now, of course, computing this squared error for all of the data points in the data set would give us something called the total squared error. In this specific example, that total squared error has a value of 100.9. Of course, just looking at the value of the total squared error, we can gauge whether this straight line is a good fit to the data or not. But because we're dealing with a bivariate data set and we're able to plot it, we can see that perhaps this is not a good fit to the data. So let's consider one other model. We're going to use the same data set, but fit it with a slightly different model. In this case, you can again see that the fit to the data is not optimal. In fact, there are quite large residuals or errors between the data set and the model predictions as indicated by the dashed yellow lines. We can again compute the squared errors for each one of the data points, and this is for x equal to 1, then for x equal to 3.5, and then for x equal to 6. And likewise, we can compute these squared errors for each and every data point in the dataset to come up with a squared error that has a value of 132.08. With the previous fit, we had a squared error of 100. This time we have a squared error of 132. And clearly this now is a worse fit than the previous model that we considered because the total squared error has gone up. So we need to decide whether we're going to stop with the evaluation of just two models or check and see if perhaps a third model might be a better fit to the data. And we'll continue to stick with straight line fits simply because the data follows a linear trend. So if we consider a third model and fit it to the same data set, this third model again being a straight line, we can compute the residuals and the differences between the model predictions and the data for each one of the data points in this data set. And you can see that happening on the screen. And if we add up all the squared errors for each and every data point, we would get a total squared error of 16.66. So recall that previously, with the first model, we had a total squared error of 100. With the second model, we had a squared error of 132. And this time around, we have a squared error of 16.66. The squared error tells you something about the mismatch between the model predictions and the data holding square. So clearly you want that mismatch to be as small as possible. So when considering all of these three different models, the model that you see on the screen is perhaps the best fit to the data in amongst those three models. So this is your introduction to regression illustrated with a linear example. Of course, keep in mind that there are many other flavors of regression that we have not considered in this specific case study, but that is something we will be dealing with at a later time.